The last thing to discuss when talking about charge is Coulomb's law, and we're finally going to quantify that force, the electric force or electrostatic force. So Coulomb's law, I'm going to show it to you in two different ways. The first way, we'll just talk about the magnitude first, and the magnitude of force on charge 1 exerted by charge 2 is equal to this constant K times the charge, the value of the electric charge on the first charge, times the charge on the second charge, divided by the distance between them, so between 1 and 2, squared. K is a universal constant, a physical constant, and we're going to explore that a little bit more later on, but for right now, it's simplest just to think of it as a constant and understand that you can use 9 times 10 to the 9. That is an approximation. I think the actual value is 8.998, but even to 3 sig figs, it's 9.00, so we can just use 9 times 10 to the 9. And then my notation of F12 is the force exerted on Q1 by Q2. And this is the expression that we use to find the magnitude of the force. And in this chapter, in your course, you'll probably spend about half of your time working with Coulomb's law. And the other, even though it's a small part in terms of the video course, and even it only gets one section in the book in your textbook, but it's just that we end up using it to quantify a lot of different problems. You still need to have the understanding that opposite charges attract and like charges repel, and that's actually where I recommend you go to find the direction, because the direction of the force, remember force is a vector, so it has magnitude and direction. The direction is that the force will be towards the other charge if the charges are opposite, and it will be away from the other charge if the charges are the same. And that's pretty much all you need to know for Coulomb's law. There are lots of different ways in the problems to give you certain variables, and then you have to solve, and sometimes you have a quadratic because you might be solving using the distance, etc. That ends up being just a bunch of different particular problems, and we'll look at some of those, but this is the basic idea. There is another form of Coulomb's law that's worth taking a look at. And for this, it's going to depend, I think, on your teacher. You might choose to do it this way if you prefer. I know when I was doing it, I preferred to work with the magnitude separate from the direction just because I felt that it separated the physical understanding. But there is a sort of mathematical simplicity, or maybe beauty, dare I say, to expressing it this way. When I express Coulomb's law this way, we again have R12 squared, we add a unit vector, R12. And this is effectively exactly the same thing as what we had before. The difference is that we have this unit vector. The unit vector is used to show the direction of the force. And we notice that we also don't have the absolute bars around Q1 and Q2 because those are actually now necessary for this equation to work out. So if I draw this, I'll have, say, Q1 right in the center there, and I'll have Q2 down and to the left. To define the direction for r hat, I want it to be away from Q1 and on a line that is away from Q2. So this unit vector would be on that dotted line. Okay, so how does this actually make sense then? If Q1 and Q2 are the same sign, then you would have, say, positive, positive, or negative, negative, and that whole expression in the middle, KQ1, Q2 over R12 squared, ends up being positive. So if they're both positive, both negative, you end up with a positive R12. And that makes sense with R12 going away from Q1, because if they're both positive, they repel, and the force on Q1 is away from Q2. If they're both negative, again, they repel, and the force on Q1 pushes it away from Q2. So those positives multiply together to give a positive, or the negatives multiply together to give a positive, and that's how it works. If only one of them is negative, which means that they're opposite, then you end up with the force vector being negative something times r hat 12. And in that case, if one of them is negative, that is when you get the force moving in the opposite direction, so that the unit vector would still point away from Q2, but if they are of opposite sign, then the direction of the force vector will be towards the other charge because they're attracted. And once again, if the charges have the same sign, then they repel, and the force on Q1 is away from Q2 in the same direction as r hat. The quantitative applications of Coulomb's law are fairly straightforward, so where it gets tricky is in having multiple forces, in which case you just add them up. You can have them in strange configurations in 2 dimensions, maybe 3 dimensions. And the key thing that I would suggest there is to always show the force direction. So always do a sketch and always show the force direction when you're solving problems. And that's going to be true regardless of whether you prefer this form or the other form of Coulomb's law. They're pretty much exactly the same thing. As long as you draw the sketch, show your force directions, then you're almost certainly going to get the right answer. And that's pretty much it for the first chapter in Coulomb's law.